Hello, welcome to the next in our series on Remanufacturing and Industry 4.0. Today we'll talk about machine learning and artificial intelligence. This webinar is brought to you by the Remanufacturers Industry Council, where we seek to advocate, collaborate, and educate on behalf of all sectors of the remanufacturing industry. In addition to our annual meeting, we are the sponsors of Reman Day, which is April 14 this year. In addition, the RIC is an authorized standards writing body for ANSI, and recently updated the first US national standard for remanufacturing. And the R&D committee brings various opportunities for networking and informational sessions like this one. A few housekeeping notes. We're scheduled for 2 hours today. Questions can be submitted throughout our time together using the Q&A icon that should be at the bottom of your screen. And I'll be posing those questions to the panelists at the end. And now for introductions. So I'm Todd Wieland. I lead R&D for the aftermarket at Cummins, and will be your host today. Our panelists include David Meek. David is the global leader for IBM's Intelligent Operations team, delivering Industry 4.0 strategy and deploying IBM's artificial intelligence and machine learning solutions. David joined IBM in 2002 and has 30 years deploying supply chain and analytic, IoT, and AI solutions to a variety of manufacturing industries. Jim Little, also with IBM, is a partner at Simpler Consulting and is leading industrial sector clients' successful lean transformation journeys. Jim began his career with lean and the Toyota production system with the GM and Toyota joint venture. His lean applications have included brownfield transformation and greenfield startups in multiple manufacturing sectors. Nenad Nenadic is a research associate professor at the Golisano Institute for Sustainability at Rochester Institute of Technology. For the past 16 years, Dr. Nenadic has been working at RIT on data analytics and machine learning applications in predictive maintenance, remanufacturing, supply chain, and renewable energy. Abu Islam, also at RIT, is a lead staff scientist at GIS, where he conducts applied research in the use of computer vision, data analytics, and artificial intelligence in remanufacturing and machine health monitoring. Tyler Marr at Southwest Research Institute is a research engineer there in the Manufacturing Robotics and Technologies Department, where he has developed a variety of intelligent industrial robotics solutions. His primary areas of emphasis are on manipulator motion planning and integrating perception systems. Simon Floyd at Google is the director for discrete manufacturing industries within the Industry Solutions Group at Google Cloud. He's responsible for defining industry needs, new solutions, and facilitating opportunities for enterprises to innovate within their value chain. Simon has 30 years experience in product design, manufacturing, and industrial software. That's a great lineup. Welcome, panelists. And with that, I'll turn the mic over to our first speaker, David Meek at IBM.
Hey, thanks, Todd. I appreciate the invite to speak. Let me share my screen. And can you see it okay? Okay, great. Can everyone hear me all right? Jim, nod if you can hear me.
Sorry. Yes, sir.
All right.
We're good.
All right. So we've already done the intros. Jim and I will talk about remanufacturing and how we apply advanced analytics and process work to improve performance. We're going to talk about the remanufacturing overview and how our things fit in there, our capabilities, and really use cases on where we've deployed these and how they're used in the industry. One of the very popular areas is around computer vision and using computer vision to deploy quality assessments, triage parts, etc. We'll talk about the different products in the marketplace, and then we'll finish with a remanufacturing case study that Jim will talk about. So with that, the first thing, just a little bit about IBM. IBM's a manufacturer. We've been a manufacturer for well over 100 years. We've actually gone through 3 or 4 evolutions in the products and things that we sell. At one point, everything we made was pretty much in steel, and we had the largest number of machinists on the East Coast. Obviously, that was before the computer and technology revolution, but we're still very active in various councils. We have a $10 billion global supply chain. We source over 30,000 individual components. And a lot of the solutions and services that we provide to our customers actually have started in our own plants. And that includes visual inspection of server components. When I'm deploying a $10 million or $20 million mainframe computer system to a major international bank, it can't fail. These systems are 24/7 and the quality is paramount. With that, we also have other things that we do. We've developed with our IBM research. We typically lead the US on the number of new patents. And then we try and use these new technologies in new ways to fix problems. And a good example of that is acoustic quality inspection. Besides looking at parts to see if they meet spec, let's listen to either the process or the parts themselves to do that. And then we also use a lot of sensoring, global position satellites, other networks to track our entire supply chain from our suppliers across oceans and even finished goods. We have a fully instrumented boxes that we ship our servers in. So we typically know where our equipment is more than the transportation companies and our customers ultimately. What we typically try and aim for is not the application of technology for technology's sake. It's really around value producing outcomes. How do we improve their manufacturing or remanufacturing performance? So how do we decrease scrap? How do we increase the throughput through the process? And for many remanufacturers that we work with, that's really what they're trying to do. How can we be more efficient in this, get more through without just adding more lines or shifts? In addition to that, sustainability has also stepped in and been very instrumental in our, hold on here, I don't think my camera's on. There we go, sorry about that. So our sustainability has come in, and so some of our clients today are asking us to use advanced analytics, the data from the shop floor to reduce their energy costs. So how do we can reduce the electrical energy by increasing throughput? We actually use fewer resources and improve the yield overall. We have a suite that came out of IBM research. It's a number of Python-based models, but they've been tuned for specific use cases. And these are getting deployed in both discrete, process, batch type industries. And it really depends on the individual manufacturing or remanufacturing process. And the 5 big ones that this tool set is used for is, one is bad quality prediction. As products are either assembled or are remachined and renewed, we gather data and build models so we can predict whether it's going to meet final quality inspection before that occurs. And the idea is, if you already know it's probably not going to meet the quality threshold or is at risk for a warranty, let's take it out and send it back to the start of the line and remanufacture it rather than continue to add value in it. A large one that we use, especially in the welding space, is anomaly detection. There's a lot of things that go on in some of these complex processes, And anomaly detection can give us early warning in that either a piece of equipment, a raw material, or something is out of sorts. Failure prediction, being able to predict when either a process or a part will fail. Process optimization is used quite a bit. If we're trying to optimize a certain process, and I'll use an example in a moment, we predict the future performance, and then we use an objective function to solve and make recommendations. Hey, you need to speed this up. You need to add more catalyst. You need to slow down the feed rate, whatever the recommendation is to bring that process back to its optimum. And then another one that is very popular right now is root cause analysis. So instead of having a manufacturing engineer for the 2 days after an event, spending time forensically looking at why a particular process failed or a particular product failed, we can build root cause analysis models and be able to get in the 90+% accuracy right at the time of event. So we can stop the line and say, hey, this failed because the fixture needs to be recalibrated. So with that, let's jump into some examples. We developed visual insights and what we call visual inspection for our own mainframe, but it's really exploded among our clients because almost everyone we know needs something to do with it. And in the lower right, we have different advantages. So we use it to look for safety features, whether people are wearing personal protection equipment. We also look at it and we can use this to identify blocked exits or warehouse rows that have pallets that shouldn't be where they need to be. We use it to assess applications. So in the automotive industry, which is big on this visual inspection, they use a lot of glues, adhesives, and sealants. And we can look at the patterns of these sealants and adhesives to see that, number one, did they work right? Do they have the right pattern? Do they have the right amount applied? And were they applied in the right location? Another example you have in here is from a seat manufacturer that provides automotive seats to OEMs using high-grade leather. They use it for all sorts of things. It's the leather before it's made into a seat, free of rips, tears, natural variations. Once it's installed, is it overly pleated? Other areas that we use this in the upper right of the lower right is a model that we built to look at crankszafts. And we spin the crankshaft and then we actually flatten that digitally. And we look for different types of anomalies, divots, shiny spots, all sorts of wear things. And that can give us an idea of, is this used and good? Is this used but needs to be repolished? Or is this scrap and needs to go to the recycle bin? And then we do this for other things as well. During the assembly or reassembly, we can look at spot welds. We can make sure that electrical assemblies have been checked to make sure that there's no broken soldering joints or that all the pieces have been inserted to the correct depth. Another one that we've used this for is for inspection of liquids. So we'll drain the liquids out of an engine or other coolant systems, and then we'll run them on a white substrate, and then we're able to look and identify any kind of objects or metal filings or things that shouldn't be in there. So moving forward, that was visual inspection. Acoustic inspection has become very popular. A lot of times this is done in environments where the visual is either difficult to do or doesn't give the type of feedback. We use this in welding. If you've been around welding at all, you can an experienced welder can listen to and know a lot about a weld, especially a clean weld or breaks or burn throughs. Those have very distinct sound generation. So we can use a inexpensive microphone. We can listen to a weld and we can identify potential problems if there are any. We use this with automotive OEMs. A lot of the final quality, a person would get in a car, drive it around, maybe on a short cobblestone patch, and listen to loose panels or other types of things. But by having actual AI models listen, we can identify the problems much faster. We can eliminate things like human speech and other false alarms, and is much more consistent. Other use cases are using a robot arm to tap a bearing race, for example, and know whether it's cracked. This is big in ceramics and others. And then we also use it to monitor rotating equipment and others to give early warnings to bearing failures, lubrication problems. New in manufacturing and remanufacturing, we see a lot of the simple use cases have been done. More and more of the complex use cases require multiple models to get the performance output as needed. Here's a case in point. This is an auto frame and body. They make frames that go into many of the popular pickups that OEMs assemble and sell here in North America. Typically for all their welds, especially MIG welds, the only way that they know if they're good or not is if they tear down the weld and cut it and etch it to make sure that it has the penetration. They might do this once or twice a shift. Well, they might make 1,200 frames. And so they just have to surmise that if it passes the QA test, all the frames are okay. And if it doesn't, they remediate all the frames. So there's a huge cost to that. And there's a huge cost to the OEMs if the welds begin to break due to incomplete welding in the field. All you have to look at are some of the more recent OEM recalls for frame welding. So we've tackled this a different way with this manufacturer. Is let's look at every single weld. There might be 300 welds on a, for example, an F-150 frame. Let's look at it using visual inspection with infrared cameras so we can see the heat and build models for the individual welds and their paths and the heat penetration. We use acoustics to listen to the quality of the welds. We use production optimization to gather all the parametric data from the weld robots, the PLCs, the weld controllers. And this is doing everything from the amount of shielding gas, weld media, amps, all these kinds of things. And with these, we use 11 different AI models to be able to come back with a 90+ percentile and say, this is a good weld, keep going. And it also uses anomaly detection to say, hey, you normally use X amount of shielding gas or a certain minimum current through the weld, and you didn't achieve that. So you need to check what's going on here or stop the line. With visual inspection, I'm going to go into more detail of that because that's used not only for automotives for final quality. We're finding more and more suppliers and OEMs and remanufacturing using this to triage a lot of the incoming parts. Is it complete? Is certain parts worn beyond repair? So that early triage can have an objective view to it and free up the people to do the borderline cases or actually make more value-added decisions for it. We have, you can do very sophisticated models with fixed cameras all over the place, but there's also a light touch for inspection. And that example is in the upper right. This is for an automotive OEM. This is in launching a new line of vehicles. The workers are new, the vehicle is new, and they end up with a lot of quality issues. And so what we've done here is we just use an iPhone. It's programmable by the end engineers. You don't need data scientists. You don't need a huge IT staff. They take pictures with the iPhone, they create a model, which will goes to the server or the cloud, where it can very quickly build an AI model, send it back to the iPhone. We inference it there. And in the upper right case, they printed a 3D model, 3D printed case with a great big battery. So these iPhones can be on 24/7 and they last about a week before the mega battery needs to be done. But these engineers move them up and down the line until they solve a problem, and the workers in that particular work cell know what they're doing right versus wrong. And then they have the ability to do this. We started with 4. That went to then multiple plants. Now they have 250 of these in operation because it's quick and it enables them to avoid large amounts of downstream problems. We use a lot of other companies' computer vision besides IBM's. We tend to use whatever the client has a preference for. We have a lot of clients on AWS and Microsoft Azure, for example. Both of those have different computer systems. Just about every provider of computer vision has pros and cons, strengths. Sometimes it's a very IT data science focused tool. Other times it's very user-friendly. But the downside of that, it can only be used for very simple type use cases. And so with that, I'm going to turn it over to Jim Little. He's going to walk through a process that we use, or a reference that we use for remanufacturing, and an important aspect as you begin to apply AI to an existing remanufacturing process. Jim?
Okay. Hey, thanks, David. I'll do an audio check with you. Coming through okay?
Yes.
Oh, perfect. Hey, and as I start, or before I just jump in, I want to thank Todd and the whole RIC team for their support. One of letting us be a part of this to share a little bit, but from our side, also a lot of learning, right? What other entities are doing, what state of the art is, et cetera, and tying us back to it. So thanks for that opportunity. As David mentioned, I'm going to step through kind of a basic use case with some real world examples of this, and then some cautions and challenges, right, on the look forward that you take with this. I'm providing in this diagram really an oversimplified process flow of what might be a typical remanufacturing operation, from where there's an early triage kind of activity and decisions made whether the asset gets scrapped completely or repairable. There's usually some kind of breakdown process, usually some inspection and decision making around those sub-assemblies or parts or components that flow from that. Clearly some cleanup kind of things. There's blasting and cleaning, other things that happen often. There's inventory between stages, of course, as these things come together. Those flow into usually different substreams where the rebuild takes place, and then it comes together usually in a typical reassembly operation, right? Putting it back together in test or verification, and then completion or rework again, back through the system. But where we've seen this, that's applied, it's really, kind of an artisan-based system usually. Every asset comes in and is almost considered unique, right? First time for everything as things begin to start through the processes. Often, the artisan work is kind of batch-based, independent bays or stations. Knowledge isn't really carried between assets through the flow usually. There's inventory that's queued up because of mismatches between stations and operations and so forth. Many unknowns and surprises, and really the connection of information between, if something has taken place on this unit early, what do we can we infer and learn from that later in the process? But things flow through. Things come through, they get worked on, and they come out, with success at the other end. But as part of, or requisite to the technology application, I want to share a success story that cleaned up some of that base level kind of work first. So David, next slide, please. Yeah, thank you. Thank you. So I've entitled this an Industry 3.0 kind of application, but really the message we want to convey in here is really building upon the ML, machine learning, and AI application, challenging organizations to think about, let's build upon solid fundamentals, right? Make sure the foundation is right before we begin to build the next layer of opportunity on top of that. In this particular case, the organization had much of that traditional flow that I talked about earlier with you, where we didn't have people engaged, we were batches that were disconnected, et cetera. And then the focus over this 15-month journey or so was really around and multiple passes through it, but building what we call manufacturing, remanufacturing fundamentals, right? Thinking of the lean principle application of visual management, flow, value add, engagement of employees, problem solving, built upon daily management systems, et cetera. And by honing that and really driving those fundamentals, footer, foundational kind of items in place at the basics level with it, crazy focus, rigorous focus around flow at tack time, we're able to establish these kind of breakthrough metrics. And if you think about, producing an asset now, remanufacturing an asset with less than 25% of the effort that it used to take, 35x on the output or the volume side. Think about the lead time satisfaction for customers that feeds all of that. The business benefit that comes from building and executing on that solid foundation is pretty astounding. So the lesson here really we want to convey is thinking about the rigorous application of the basic principles in the industry 3.0 level work before stepping into, or is requisite to adding on top of and leveraging beyond with that piece into the 4.0 realm. And I'll give an example now of even better or build upon with that, if I could, David, on the next slide. So same basic flow is shown at the bottom. But the real adder or differentiator in this, and what we think is so exciting for this group and the audience thinking about it, is as that base gets honed, where do we need to add or consider the technology layer, whether we call it ML or AI or 4.0, but where do we layer that in that delivers on a business need to establish and enable flow of the product overall that delivers that to the end customer? Right? So those familiar with value stream analysis and value stream thinking, it's the flow of information. And where can we apply the intelligence to get real-time feedback into the operations that support the flow that provides the value to the customer? And all of those insights, whether it's from the acoustical or the visual or thermal or energy consumption, et cetera, around that, where are those point solutions going to enable flow through the overall? For example, technology on operation B can help improve that, but if that only bogs up at operation C or D downstream, are we really providing value to the end user through that application? What liberates the capacity is the key we would think about and create that flow. But everything from the cycle time to feedback on asset-specific instructions. We learned this earlier on the activity as we were doing teardown. Let's consider or look at the other side when it comes through on the reassembly. All of those thoughts tie back in very strongly, I believe, to the idea of where the application is most appropriate, but certainly connecting knowledge so it flows with the unit and the product to the people who add value, the operators in the disassembly, repair, or reassembly, so they can make better decisions faster, higher quality output, and it really just leverages it even beyond on the business outcomes that you're trying to drive. So pointed application, value stream thinking, built upon a foundation of tech time-based flow is really where we're seeing this great jump-in opportunity to take it even further beyond. So thank you.
Thanks, Jim. And I think the bottom line here is getting that bottom line savings and value add. And I view these two components as two sides of the same coin. And a current client of mine, in terms of applying quality and AI, didn't want to pave old cow paths. He wanted to both optimize the process and operations while applying leading edge machine learning and deep learning and other AI models to exponentially improve their business performance. So with that, just want to say thank you for inviting us to speak, and we'll be around to answer questions via chat.
Thanks.
Excellent. Thank you, David and Jim. Next, let's turn it over to Nenad Nenadic at RIT.
Hello, hope everybody can hear me okay. Let me just make sure that I turn this into a presentation.
We can hear you.
Can you hear me? Yes, okay, and you can see my screen. So this is our Sustainability Institute at RIT campus. I'll just say a few words about our organization. We have been doing reman, industry-driven reman for the past 25 years, with the key areas is design for reman, materials, restoration or repair, condition assessment and inspection, cleaning processes, and life cycle assessment. We were leading the team that proposed to the DOE the Remade Institute, which is now promoting transition to more circular economy. So our the material that I'm going to present today is a part of a Remade project that was a collaboration between Caterpillar, CoreCentric, and RIT. And this specific topic will be machine learning for health assessment of LEDs that are on printed circuit boards. So this is more like it's a kind of more specific and a little bit more in detail, far less in breadth than what David presented, but it's just kind of like maybe one can see it as a template for some homegrown development of machine learning. So the way that we understand this business case and motivation for the machine learning is to enable this automation and primarily improve efficiency. Those are the somewhat widely considered good starting use cases. So in this case, to speed the processing of PCBs. Specifically, these operations like CoreCentric are largely manual right now, and they rely upon training technicians, and some of the tasks are kind of become tedious, which is over time, they make more errors as the day progresses because of the repetitive tasks are not best suited for people. So one of the commonly accepted approaches to start with a relatively easy problem or low-hanging fruit that would allow us to complete and make a difference over a short period of time, and then also to give the stakeholders an opportunity to see the process, and then we can tackle maybe higher value problems in the next round. And this example that we're going to go through will illustrate this process. So as I said before, the specific goal here was to take pictures of PCBs and then isolate individual LEDs and then assess their health. We have 3 PCB types. 2 of them are currently being assessed using visual inspection, and the third requires electrical test. And the motivation is kind of just as was described in the previous slide. Technicians take some time to train. These skills are not always perceived as high value skills, and the tedious nature of some of these jobs are like a good opportunity for machine learning to improve the speed of operations and even long-term accuracy. So I mentioned again that there are 2, from technical perspective, there are 2 machine learning models, 2 tasks. One identifies LEDs on a picture of a printed circuit board, and the second one assesses the degradation related to that LED. So our approach was to kind of put together a quick end-to-end workflow, so starting with image capture, and then this isolating LEDs from the pictures of PCBs, and finally adding the health assessment. So we put this workflow quickly and then iterated to improve upon the solution. And we'll go through some of these in the next slides. So a couple of words related to what's required to start machine learning. We are this software certainly is not the barrier to entry because there is a really impressive set of open source software tools, primarily in Python scientific ecosystem, but there are others, including Julia, R. There are other alternatives, even though I think Python is, not just me, I think it's widely understood that Python is pretty much the largest. It's very rich set of tools. It's specifically rich in machine learning tools with general machine learning algorithms in scikit-learn, a couple of different image processing / machine learning libraries such as OpenCV, and then the latest or the most recent revolution that took place in deep learning or large neural networks. There are two, I mean, there are some others, but there are two really leading excellent frameworks, TensorFlow from Google and PyTorch for Facebook. We have students that work on our projects and they come from different backgrounds and they use both of them, and we use them, in our organization, we use both, but they are pretty much have very similar capabilities. And one of them is they already have large pre-trained models that could be used to leverage the development. And in fact, we always try to do that. And in a presentation that will follow that Abu will present, you'll see more about that. So now when it comes to data, that's a little bit of a different story. In some rare cases for industrial applications, to our knowledge, there is good data. For the most part, people have to collect the data, and that takes some effort. And especially when we want to do the high level applications that go beyond anomaly detection, when you want to do the recognition, we need to provide labels or the ground truth for the data. So in this case, we wanted to detect healthy from degraded diodes. So for that, we certainly need to know what's the true state of degradation. So this is our data set. It was not too large. We have 44 boards, just over, somewhat over 2,000 diodes, and about 3-to-1 ratio of healthy to degraded. That's for degradation. Usually there are far few examples of degradation. So in this case, it's almost better than in most cases. And then we took multiple pictures of individual of the PCBs under slightly different lighting conditions, rotation, and so on. And then again, I mentioned before that labeling the state of health can be a little bit of a challenge. It takes effort, and even the practitioners that are, or domain experts that are doing it today, they don't always agree in assessment of the state of degradation for individual specimen, in this case, diodes. So now I'm going to spend a little bit more time on this localization or isolating the bounding box associated with individual diodes. In this case, we did use an existing model that's maybe not the most popular model, that's called UNET. It was developed originally in the context of medical imaging, but it's found to be really good for relatively limited data sets. When we attempted to use pre-trained existing models, we didn't have as much luck as with something that's a little bit more fine-tuned. In addition to that, we use image processing. And here is a block diagram of our process that we developed to expand localization to a new type of the diode after experiences on the three diode PCB types that I showed pictures of earlier. And the gray boxes are fully automated, and these salmon or orangey boxes require some human in the loop. So there is a little bit of effort to generalize or extend the solution to additional PCB types. The performance for localization, we were very pleased with. Here are a couple of examples of good, between good and very good. We have about 98%. The next step was health assessment. And I kind of include a little bit of details here, how we approach this. It starts with initial data collection. In our case, those are LED images. And then we try different models. Then we train to adapt the models to the data, and then we validate it with the different data, and then iterate with a couple of different models. And sometimes we realize that we need more data, so we expand the data set. And then usually before that deployment, it's good practice to use a third data set that has not been used before. And then after deployment, there is opportunity to either expand the solution or sometimes to adapt it. So for instance, in predictive maintenance, models are more sensitive if they get recalibrated between the maintenance intervals. So, so here is the training. This is maybe a little bit too detailed, but this is just to kind of illustrate what the process is. We typically split the data into 70-30 ratio for training and for validation. In our case, we have to be it's often the case that the physical objects, in our case, diodes, they have to be either fully contained in the training data set or in validation data set. If they're split between the two, we will get misleading performance, misleading good performance, because these are very large models and they can easily memorize everything and then generalize poorly. So that's why often the third data set, when we see what the validation is needed to get us better performance. So we experimented with a couple of simple models. First, support vector machines, gradient boosting and random forests, and even repeated experiments multiple times to get better sense of what would be the field performance. The best performance was obtained with CNNs, which is a neural network model. So it stands for convolutional neural networks. And we got the best performance using our own model. We usually try to apply transfer learning because there is that's a kind of a shortcut. It's very effective, and Abu will tell you a little bit more about that approach. But for this specific case, we got better performance using models from the outset. And so just to get an illustration of the performance, we got, when we fixed the false detections to less than 5%, our detection was nearly 99%. So that was, we were really happy with that. And now we are building the fixture to enable this kind of like to put it on the reman floor at core-centric. And as we were kind of thinking about similar machine learning problems, core-centric identify the same problem that David talked about in the previous presentation is triaging or identifying these PCBs that are perhaps irreparable and they have too much damage. So we developed a little tool that would allow them to capture that information so that we can take some training data and label or annotate faults so we can, in the next iteration, tackle that more advanced problem. So in summary, a good candidate for machine learning is a repetitive task. There is a rule of thumb that was proposed that if a human can use vision for 1 to 2 seconds, it's typically a good machine learning problem. Starting with low-hanging fruit is for an organization that hasn't done any machine learning on their process is best approach. The performance can improve over time, but typically requires, if it's kind of like homegrown solution like we have here, not a product that IBM was describing, requires somebody with either, or at least with machine learning expertise and occasionally domain expertise. So we have good results with our LED example. And this is not a fully completed project, but we thought that it would be interesting to share with this community. So Abu, can you take over?
Sure. So can you hear me and see my screen?
Yes.
Great. So I'm going to talk about image-based machine learning for automated sorting of remanufactured automotive core parts. The motivation behind this work is that global automotive part remanufacturing is a growing market. It is projected to be over 150 billion by 2026 at a 7+% of CAGR. And as you can see that all kinds of automotive parts are slated to be remanufactured. It starts from engine parts to electronics to body parts and whatnot. So it does warrant attention from the research community to improve its accuracy, efficiency, and to some extent, safety as well. So how are these parts collected? Traditionally, these days, the cores are essentially the automotive parts that are coming in, cores, are collected by what is called core brokers. And typically, they receive these parts in pallets, they're intermingled, and that's how they delivered these to the remanufacturers. And what the remanufacturers have to do is then almost manually first sort this by the types. For example, is this an alternator? Is this a brake shoe? Is this a fuel injector? And then they have to sort them by the model numbers. And it takes time. Typically, we have heard from one of our partner, Diesel Core, that it takes maybe 2 to 3, it takes in a minute, it can do 2 to 3 brake shoes. And their accuracy is probably in the low 90s. So they'd like to improve the accuracy and reduce the time in this classification. So our goal in this project in the first phase is that can we separate or classify these parts into its broad categories? For example, okay, these are brake shoes, these are fuel injectors, these are alternators and whatnot. That's number one. And then within each type, can we say, hey, this fuel injector came from Ford, this is from Bosch and whatnot. Can we make this kind of classification? And of course, we have to improve the accuracy to over 90%, and with about 2 to 10 seconds per sorting time. That's the kind of guidelines we got from our partner. And in the long term, we'd like to classify these components based on their conditions, how worn out they are and whatnot. And of course, we also want to identify if our system hasn't seen a certain part that comes into the inventory. So of course, we are using, as the title said, we are using a vision-based system. And for that, we need a lot of images for these parts. And typically, we don't get them from the field. So we have to kind of generate them ourselves. So as we get these parts, we generate we captured over 12,000 images. And our initial parts that we have selected were brake shoes and fuel injectors because they come in large volumes. And one of the important ones to classify, that's what we have learned from our partner. And the way we capture the images we use the rotary table. So we can collect images at different angles, at top views, at isometric views. And because as the parts come in, as we are putting them in any kind of transport system, we cannot really say, hey, it has to be in this particular orientation. They can come in whatever orientation that the user puts it in. So we have to be flexible to that. So we capture images at different angles, and we also capture images at different lighting conditions because we also expect that is going to happen in the remanufacturing floor as well. So like I said, we are using fuel injectors and brake shoes, and these are the different models that we have in our inventory. And for each one of these categories, we have about 4 to 6 repetitions of the same model numbers. So that's the kind of parts and data that we're dealing with in this work. So as Nenad alluded to, we are using transfer learning to improve our efficiency. And what that is essentially, companies like Google, Facebook, they deal with millions of images to recognize face, objects, animals, flowers, and whatnot. And not only they can classify, they can identify. And they have developed very sophisticated model. And in their model, the early portion of the model, essentially what they do is they extract features from those images, right? With the horizontal lines, vertical lines, curves, circles, right? These are the kind of features that are used to classify objects. So since they have a huge database and they have created this model, it makes sense that can we just reuse that portion of the model in our work. Of course, their end goal is to classify whatever they're working on, whether it's animals or faces. That's not our objective. So in transfer learning, we take part of their model, which extract features from the millions of images, and we bring it to our model. And then instead of their database, we feed in our database of automotive parts, and we try to extract features from them so we can classify. So that's what's called transfer learning. In our particular case, we've used inception transfer learning, and some of the advantages for this method is it requires less training data. Of course, with automotive parts, we will never get millions of images. So, but then with the pre-trained model, we kind of circumvent that problem. It speeds up the training process, and of course, we get higher accuracy. So moving forward, this is kind of the overall model that we have used. There's a first model that we use that classify objects between brake shoes and fuel injectors. And then once we have categorized them into two categories, we bring in detailed models of brake shoes and fuel injectors, which kind of subclasses them into individual models. So that's the kind of overall structure of the modeling that we have here. Let's look at some of the results. As you can see here, that to classify between brake shoe and fuel injectors, we do very well. They're very, very happy with the results, over 99.9% accuracy and in classifying between two large groups. Going forward, how about within a class, for example, how well can we classify a fuel injector into different models? As you can see there as well, our accuracy is over 99%. And of course, some of the errors we make is when these objects are looking very similar. And even after taking images up into all these angles, if we cannot capture the difference between them, we make errors. But still, we were very happy that our accuracy is over 99%. Going forward, for brake shoe, we get over 99% accuracy. As you can see, that some of the errors that we make, for example, if we take this particular case, these are two brake shoes, 4707 and 4515. These two brake shoes are identical in every way except for distance between these two holes. They're like 1 inch difference. So as you can see that if our imaging system does not capture that difference, it will be very hard to differentiate in our classification. So those are the places that we made error in this classification. So how would we deploy them? So of course, Diesel Core or any remanufacturer would have their own front-end system with their ERP, their GUI and whatnot. So they will use that. And then they will also have their end binning system that could be conveyor-based, that could be robot-based and whatnot. We have developed a prototype of this, what goes into the middle. Of course, parts will come in the conveyor system. We will have our multi-camera imaging system. We'll capture images and we'll feed those images back to an analysis tool based on Python, as Nenad explained, and that will classify those parts into different categories. So in our labs, we have put together the prototype. Hopefully the video is working for everybody. So this is a conveyor system, and these are our multi-camera gantry. This camera will take the top view, and these three other cameras will take the isometric view of the object. And in this conveyor, the operator will place the parts as they're coming in from the pallets. And these parts will go under the camera. In this particular case, as the part goes under the camera, it's stopped by these sensors. As the sensor detects, we stop the conveyor and take the picture. And as you can see, we detect this and identify this as a fuel injector. Then a brake shoe comes in. We identify this as a brake shoe, and we continue. Of course, we are classifying them into the categories as well. It's giving up that information in the details as well. And as the parts will go to the end of the conveyor, of course, they'll be picked up by a robot or additional binning system that our remanufacturer will have. So this is the prototype that we are maturing in our lab, and this is the system that we want to deliver to the remanufacturer to make it part of their system. In summary, going forward, our next steps, of course, is to demonstrate the latitude so we can basically detect parts under all kind of manufacturing environment. We want to detect out-of-class data set. We want to investigate other kind of parts in addition to brake shoe and fuel injectors like alternators and whatnot. And of course, we want to work on the end binning as well, some kind of cobot-based separation of the parts as after they're done with at the end of the conveyor system. So this is what I wanted to present for this presentation. Thank you.
Excellent. Thank you, Nenad and Abu. Next, let's turn it over to Tyler at Southwest Research Institute.
Oops. All right. You should be able to hear me. You should be able to see my screen.
Yes.
All right. So today I'll be talking about leveraging deep learning in industrial robotic systems and talk about some of the work that we've done here in my group at Southwest Research Institute. So what is deep learning? We've heard that term thrown around a couple times today. So let's kind of take a broader step back first. We have the overall encircling artificial intelligence, which is basically programs or algorithms that are able to do tasks that generally are thought to require human intelligence. And then you have a subgroup of that called machine learning. And this is algorithms that can improve by using data. So we see a lot of that. And then one step further, you have deep learning, which is a subset of machine learning. And deep learning is machine learning achieved by using artificial neural networks with multiple layers. So typically, I think when we hear AI and machine learning, those terms thrown around, a lot of our minds immediately go to deep learning, which is kind of simulating brain architecture and using neural nets to that are these really big structures to learn how to do different tasks. So what do we do at my group at Southwest Research? So what we do is create a lot of scan and plan systems. And so I'll define that in just a little bit. But what these systems accomplish is different spraying applications through either painting or a grit blast system. We do a lot of material removal, so like sanding of materials or grinding. And we also do inspection. So this may be a non-contact inspection. And we do several other things that fall into these different broad categories. So a very wide range. And we accomplish this through a process that we like to call scan and plan. So scan and plan is kind of like what the name implies. It's basically you do a first step of scan. So we have a sensor on an industrial robotic system. And we use this sensor to localize, either localize a known object with 3D sensor, or we can actually generate a mesh of an unknown object at a known location. And then once we have this object and we know where it is and exactly what it is, we can actually generate specific waypoints on it. So say it's a sanding application, we say, oh, we want to sand at exactly these points. And then once we know the waypoints, we can plug this into a computer program that will output a robot trajectory to say, okay, to hit all of these waypoints, we want to do this exact motion with this robot arm. And then sometimes if necessary, there's an inspection process to follow to see if we are finished with the process or need to keep going. So a nice summary of that can be seen in this video. So we'll see a big blue robotic arm, and then at the end of the arm, we see this little gray object, and this gray object is a compliant end effector. So this is what you'd put a sanding tool at the end of this, and then you actually have a little bit of compliance, so you can push against the part and don't have to be perfectly precise, and you can input a specified controlled velocity of the sanding spindle and required speed. And so the first step, like I mentioned before, is the scan step. So here we have a 3D sensor on the end of the robot arm that's moving across and generating a mesh with a pre-canned path of the robot. And so robot's never seen this part before, and we just generated a mesh, and then we load it into another one of our softwares that allows us to generate waypoints on the part. And so now you can see there's a series of waypoints. And now once we have those waypoints, we can pass those back to the computer program and actually generate a motion plan. So now going from no knowledge of what the part was, we actually have a robot that's ready to execute a trajectory and start sanding the part. So where does deep learning fit into all of this? All of those tasks I described, yes, require things that fall into the category of AI, but I said I was going to talk about deep learning, and there wasn't really any deep learning specifically in that process. So here again, we have an overview of the process I just described, where you find an object with a sensor, generate waypoints, motion planning, and then inspection. But for each of those steps, there are ways that you can implement deep learning, and there are times when it actually makes a lot of sense to use those processes. So with finding object with the sensor, maybe you want to crop the live point cloud that's coming in with semantic segmentation. And I'm going to throw around a couple specific deep learning terms here, and I'll explain them later in more detail. And then, or maybe you want to generate waypoints specifically on specific areas and you want to identify those areas. You can do that with semantic segmentation. Or maybe your robot planning is taking a long time or is really complicated, and you could leverage reinforcement learning to use to solve those problems. And then also inspection, we've seen a lot of examples of image classification. This is a perfect candidate for that as well. We can use image classification to really help inform the process. So I'm going to highlight these 3 areas here and go through a specific example of where we've actually implemented these systems on a robot. So first scenario, generating waypoints with semantic segmentation. So this application is for a welding robot, and you have this scenario. You have a worker who will take 2 pieces of metal and tack weld it together. So the weld needs to be finished, but they just set the part down, and the robot needs to find the part and needs to find exactly where the weld location is. So in general, the worker will be able to set it in a pretty consistent spot, but you can't just hard code the path to finish the weld, because the part will probably have some variation. The parts will be inconsistent. The placement will be a little inconsistent. So our solution is to use deep learning to locate this weld in 3D space and then generate the path plan. So how are we going to use deep learning to do this? So we can use what's called an RGBD camera. So this is what was used in that first video I showed where we generate the mesh. So this is basically red, green, blue plus depth camera. And so you can put these on a robot, and now you have a regular image being output from the camera, but you also, along with it, have what's called a depth image, which instead of red, green, blue values being populated, you have depth data being populated. So how far away is that point? So we can then use semantic segmentation to find the weld. So what is semantic segmentation? It's basically you take in an image and you label every single individual pixel with a category. So in this instance, we'd label every pixel, is this the location of where a weld should be, or is it not? And then once you have all of those labels, you can actually map the 2D data onto the 3D data that we've generated. And then you can extract that 3D data, if you know where the location of the camera was at that time, into 3D space. And so now you just do a pass over it and you can know exactly where the weld needs to be in 3D space. So what this process would look like is you have a scan pass that finds the weld. We extract the weld location into 3D space, and then we can generate waypoints from that weld location and then motion plan from those waypoints, just like we were doing before. So here's a video that's going to showcase that running through. So on the left here, you can see a live feed of the camera. On the right, you can see this robot, which is looking down at where we know this part is going to be roughly. And so this top image shows the regular image that we're used to seeing in black and white. And this bottom image shows an overlay of the top image, but specifically highlighting where the weld is. So where this black line is exactly lines up with where the parts are fitting together. And where white is, that's saying, oh, we don't want to weld there. So if I play this, you'll see the robot move across and then identifying where the weld is. So you can see it move with the picture as it's moving. And we're generating all that information, translating that into 3D data. And so now here, you can actually see we have a point cloud of all of these points that we captured, and there's a black line going across the middle. And this is saying, hey, identified the weld is right here. And in addition to doing this, we actually generated a mesh at the same time. So we can say, okay, there's an object here. We want to avoid hitting that. And then immediately we can just generate a toolpath from that, a set of waypoints. And then once we have those waypoints, we can generate a robot motion plan, which you'll see a preview of right here. So now the robot's ready to weld. So this part could be presented in several different orientations. It doesn't have to be precise, and the robot can find it and finish it. Next application we have is motion planning with reinforcement learning. So say you have an application where you have confined space that the robot needs to perform an inspection in. So the scenario is a robot enters a tight space with a large end effector, but the base of the robot always starts in a different spot, and you're always using the same geometry. So you have the same type space, same end effector, but your robot's going to be in a different spot relative to that tight space. So the problem is you can't hard code the path, because while it might be a complex trajectory, it's going to change every single time you come to do the inspection. And so this means motion planning in a traditional way can take a long time sometimes. So the solution is to use deep learning to create a model that can solve this problem quickly and repeatedly. So how can we do this? We can use reinforcement learning. So reinforcement learning is a method of learning that basically you train a system by rewarding good behaviors and punishing bad behaviors. And over time, the model will learn to do more of the things that lead to good, lead to more rewards. So you set up a simulation of the environment, set up many possible configurations, and then you create a reward function. That's one of the trickiest parts of this process. And then you run through thousands of iterations offline in simulation until it has learned how to actually perform the task. So here we're going to see a robot with this large barbell shaped thing trying to fit into this slot. And so at first, the robot doesn't have any idea what's going on. It doesn't even really recognize what the goal is. It'll just get rewards as it gets closer to trying to get this part into the slot. And so you'll see it randomly move along. And as this episode counter moves up, you'll see it start to get closer and closer. It'll start to begin to find its way to the beginning and then slowly find its way through the slot. So at the beginning, it's moving around, just kind of randomly exploring the space. Oh, and after a little bit of time, it's starting to say, oh, I should probably go up to this area. And then a little bit longer, it starts to figure out how to actually get into the slot without colliding. And then a little bit longer still, and now it's actually figured out how to get all the way into the slot, into the bottom. And so once we have those results, we were able to smooth out that data because it's still a little shaky, and get these final performance results. So we can see it quickly planning from all different configurations, from all different positions. And then we further trained this on different parts as well. And it was able to learn how to navigate those parts too, even including really complex, tricky shapes where it had to loop around multiple times. So this can be leveraged for many systems. And then finally, we're going to talk about inspection with image classification. So this is a sanding robot. So this is kind of the robot that I showed the very first video of. The scenario is a robot is set to sand the top layer of a large part, but underneath that top layer is a sensitive layer that must not be damaged. And you have varying thickness of the top part, and the robot must reliably sand to completion without causing damage. So this is a relatively simple task for a human to perform. They can just see, oh, that area is sanded, let me not sand there anymore, or this area needs more sanding, I'll focus there. But trickier for a robot because you can't use a robot in a traditional means where you hard code a path and say, oh, do 5 passes over this part. Because if you do that, you might just damage the part. Or if you're too conservative and say, oh, we'll just do 1 pass and that'll be it, then you're going to have a lot unfinished. And then you also need expert judgment to determine what qualifies as fully sanded, and that varies from system to system. So our solution to this is to use deep learning to create a classification system that can identify sanded areas and then skip over them. So how can we do this? We can use a 2D camera attached to the end of the robot, and we can collect hundreds of images for training the system. And then we also have to deploy a system that's easily trainable in deployment, because anyone with experience working with these classification systems know the system is highly sensitive to the environment. If the lighting changes, or if you don't have a huge range of environments in your initial data set, it'll fail whenever it comes to, oh, I trained everything in a really dark room and now we're suddenly in a really bright room, or we have reflections off the part from the lights. So that's causing misclassifications. So in order to enable this easy training, we created a tool that actually allows users to quickly go through and automatically generate these images and basically generate captchas that you'll go through and label as, oh, this is sanded, this is not sanded. So here you'll see an example of me going through and selecting all of the boxes that deem as sanded. And so this way you can quickly export all of this data and then retrain the network. It also allows you to, if you notice it's neglecting certain areas or it's marking things as sanded too soon, you could go back in and retrain the model off this automatically generated data. So it should be quick and easy to use, and just logical to interface with. So what does the overall pipeline look like now? So this is the beginning of this is the typical scan and plan fashion plus a little bit extra that we added on. So we scan the workstation, generate a mesh, create waypoints for the robot to stand, and motion plan to stand part. So that's what we showed before. It's pretty our standard operating procedure. But now what we do is while we're sanding, we actually use that camera and the live data to classify waypoints as sanded or unsanded. And then once we mark a waypoint as sanded, we remove it from the list. And then we replan the motion to sand only the unsanded waypoints. And if you repeat this process over time, eventually you'll get down to where everything is sanded. So if we look at picking up where we left off, we have the robot executing the motion that we were executing before. And now we'll go into a live feed of that robot actually executing that motion. And so you can see all these blue dots represent the waypoints, and the boxes are classifying the live data. So we can see there's a sanded section in the middle there. So now the robot goes back and it skips over that sanded section. So as you can see, if you repeat this process long enough, eventually everything will be sanded and you don't have to worry as much about damaging that sensitive undersurface. So that's all I have today. Thank you for this opportunity to present.
Thank you very much, Tyler. Next, we'd like to hand it off to Simon at Google.
Yeah, thanks, Todd. My video is not starting, but it doesn't matter so much. I can just jump directly into the presentation if everybody can hear me okay.
We can hear and see things.
Hear and see, that's how I like it. Perfect. All right, so allow me to get started here. First of all, thank you very much for the opportunity to come in and speak with you again. I think this is my second time round to be with everybody, so I certainly appreciate being able to come back. And for today, over the next 20 minutes or so, I'd like to talk about something a little bit different, is the application of data as it relates specifically to remanufacturing. All right. Let's get things kicked off here. To begin with, I'd like to start with just an overview of what we're doing in the industry, just for orientation, is that not always is it well known all the different types of things that we do for the manufacturing industry. So I'll take a moment to go through that. Then importantly, I will talk about the types of data challenges that we have in the industry, what the types of opportunities are as I see them, and then finally, why kind of a digital thread really matters for this industry, I believe, followed up with some overall recommendations. All right, great. So to kick off, first of all, what do we do in the manufacturing industry? So actually, we've made a number of investments in the industry over the years, probably starting with just our own core need. And so, as you would know, we sort of manufacture consumer devices. We also manufacture all of our server hardware and so on for the data centers. So we've learned a lot from our own manufacturing, and very much in our style is that we're very sort of open to sharing that. In fact, we base a lot of our technology decisions on how we're going to share it with the rest of the world. And it becomes, if you like, a foundation for us as to how we work. Along very similar lines, we also participate in other industry forums, such as OPC Foundation, as an example, and we make a contribution back to their data standards and protocols. We also, of course, develop our own applications that we can share with you, which we consider to be an accelerator. So where we've had some of that learning through, whether it's industry consortia or whether it's through any number of our engagements that we have, we like to package it and try to make it as easy for other people to use and sort of focus in on the business application and try to make the technology part as simple as possible. Furthermore, across the portfolio, you'll see other products there, as Google Glass as an example, which is a topic that I talked about before, which was augmented reality, and then sort of closing things out with some of the other investments that we've made across the Alphabet portfolio, such as Intrinsic, which is focused on artificial intelligence for robotics. And in some circumstances, we also have core technology that we use in our own products that we offer independently for people to use, such as the radar sensing capability called SOLI. So to continue on, what do we do with this type of technology? Well, here's just a very quick visualization of our line running and sort of manufacturing a Pixel 4a phone, so a couple of generations older. Obviously, we've been doing this for some time. I can show you this version, but I can't show you the current ones. Just some of it we have to keep secret. We can't be totally open with everything. But here's an example of how we use vision inspection types of capabilities. And one of the reasons why we like this style is it's very flexible. So we can create an iteration, sort of a new design, which might be accommodating a supply chain restriction that we may have, or it's for quality improvement or new features or functionality. And then we can modify our quality inspection almost on the fly. So it gives us a lot of agility and efficiency. I wanted to mention that because that type of technology is what we feel would be really pertinent for this industry as well. But first of all, to get there, I need to kind of describe what some of the problems are as we see it. And for me, this is kind of going back in time a little bit because I've spent a few years working in construction machinery equipment, in particular kind of data analytics and AI in this particular space. And so the sort of challenges of remanufacturing are really sort of prescient for me. I think I've felt a lot of this personally myself. And so then it's a question of sort of how to solve this problem sort of all up, rather than just sort of discreetly going after one or two things. I'm thinking more holistically, how do we go about this? And here is really, pardon me, the way that I've sort of framed the really big problem. If this machine is coming back for remanufacturing, so if the OEM is going to purchase it on the open market, or they're going to ask for a customer perhaps to come and do a trade-in or something of that nature, they want to completely remanufacture the machine and put it back into market, there are actually a lot of unknowns. And one of the things that is probably most frustrating for even people if you're thinking about buying this machine before it goes to remanufacturing is that the information that you have is actually pretty small. And that's true for the manufacturer. There's not a whole lot reported here, with the exception that they were kind enough to call out the fact that there happens to be a diagnostic trouble code. Now, whether that's significant or not, you would need to understand what that code actually is and then what the impact would be for you. Now, that's very much the experience you'd have if you were a buyer. But if you're the manufacturer and getting this back, is that really a big concern for you, or is that really an easy fix? You have the same type of questions, but you've got a whole other scale because you're thinking about putting it back as if it were new. But it then becomes a challenge of what do you replace and what you don't, because you need the efficiency, obviously, of only replacing what is absolutely necessary so that you can then increase your overall margin of the product that you put back into the market and still want to retain its overall quality, because after all, this is your product and it does represent you. So kind of continuing along with the same piece of equipment, a couple of things that we sort of notice about this in particular is that it doesn't come with a whole lot of history. We don't know a lot. Maybe it would have maintenance records if we can find sort of the dealership that it's been to, or if we can find someone who's been taking care of the service. Maybe that's kind of manual records that we can find, or perhaps there's something digital, a digital record that we might be able to locate, but it's not sort of carried along with the equipment. We can't really see it to really know. And that could be a really big decision point for us as to what we're going to do up front. So if we're trying to create like a risk model, if you think about it that way, what do we believe we need to replace before we actually start inspecting and tearing down a piece of equipment? We don't have a lot of information. And often that's actually excluded. We just go to standards of practice. We go in, we start to do a tear down and inspection. Very costly, takes a lot of time, takes a lot of labor. The other thing we could say as well, it's not as if we're without data. We could go to, say, a diagnostic computer, we could go to ECU, and we could download some information. These systems generally don't do a particularly good job of recording. You may get whatever the most recent trouble codes were, or you may get some sort of identifier, but you won't see all the other ones that occurred. They will have been overwritten. So the amount of history that we have there is actually very small. So then if we take it a step further, what would we want to know if we had the opportunity before we start any type of refurbishment or remanufacturing? And this is where I think that there's kind of an interesting play to think about more like the world's data. And you know, kind of self-servingly, this is kind of what, you know, Google Cloud, we believe we're good at doing, is bringing this information together. So now it becomes a question of how much of that is going to be useful, the world's data, for this application. And it doesn't take too long to kind of put it together. If you just ask that question, what would I actually like to know? First thing I'd like to know is sort of where and when and how is it actually used? And so the kind of geospatial information is very interesting. Was it hot climate, cold climate? Was the humidity factor? Was overall temperatures during its operating time? Where was it moved to? Different locations of this nature. And then, of course, were there any kind of incidents that occurred that, you know, I can't see? There is, you know, generally no type of you know, telematic for that we can gather off the machine. And yet that would be sort of pertinent to understanding what we may need to fix, as an example, especially if we're trying to be efficient in our overall operations. And then we're very challenged with what is the kind of maintained condition of the very critical and expensive components, say, like an engine. So the information is out there, and we know that. Some of the equipment manufacturers have really advanced telematics. They have a very good history of things that occurred, but it becomes a question of how fine-grained is that information to make it useful for the way that we would want to inspect, understand, and predict what its forward-looking performance would look like. So that's really where the application of data analytics, and in particular more advanced analytics that you would have with machine learning, really comes into play. And what I've put together here is just a visualization of one of our tools that does a lot of this work automatically for you. So you provide the data stream, and then it does a very good job of automatically working out where there is anomalous behavior. And it also can give you that sort of projection or a prediction forward of what performance will look like, given the historical information that it already sees. Why I think this is so critical is that it doesn't if you like, predicate itself on having like a very large onboard computer to gather the information, although this would frankly be quite useful if we had it, but we don't always need it. We can just run through a test procedure of the equipment itself and then take that data stream and learn from it. And this could be the difference between what is a good and bad part. As an example, in a testing procedure, if this piece of equipment came in, it did not have any diagnostic trouble codes on it, and so it looks like it might actually be good to go, just taking the time to do secondary inspection may actually reveal that a particular component should be replaced, because its longevity perhaps is much shorter than we would expect for the warranty that we'll provide on the equipment as it was remanufactured. This can also be another way to kind of certify the equipment for quality, because we can project forward what that performance will look like. And if we begin to see anything that does not meet our specification, then that would obviously be the opportunity to take it back through another cycle, or it would perhaps even indicate that we should just do perhaps just an OEM replacement rather than a refurbishment. The important thing about this is that the tools are there that don't require much data science, if any, because we've tried to make that sort of as easy as possible for people. But if you're so inclined, you can go as deep with this technology as you wish. And so we kind of catered to both ends of the spectrum. So let's just take another look at the technology that I showed you when we were sort of looking at printed circuit board assembly, and how can it be used in other circumstances. So what I've done here is just take just a Cummins, just a sort of like engine head, so valve train, and I was just sort of looking this over myself just on the image, and I was just looking for all the different types of things that can be detected very easily as either part of a remanufacturing step or part of a manufacturing step, and so one or the other, and then how it can be used to also kind of be instructive for an operator when they're going through a procedure of refurbishment or some other type of action that they're taking. To help, what we have done with our technology is pre-train 3 models so that there is a minimal amount of sort of image data that's required in order to get there. One of the big challenges of the industry is that with machine learning, generally, it requires quite a bit of information in order to get a really accurate outcome or to be able to kind of predict forward what performance will look like. So in style of not wanting to make that too difficult for people, we've sort of pre-trained 3 circumstances. So now around about 100 images or maybe even less, and you're getting the sort of accuracies that you're looking for. It really looks for 3 circumstances. It looks for assembly conformance. So if something is actually in place, and if it is in place, is it aligned correctly? The other that it looks for is just simply, is there any type of surface type of defect that might be there? For an object, as an example, scratching, things of this nature that would generally occur on the surface is one condition. And then finally, just by telling it what is good, it can work out what is not good or what is just an anomaly and start to flag those individual areas. Now, behind this, there is a data component to it. So it publishes what the performance of the machine learning model is, but then it also starts to publish, in particular, where there might be a false positive that's occurred, where retraining might need to be done on some of the information. And importantly, there is the human in the loop. And the reason why I like to identify this is that even though we're sometimes afraid that the machines are going to take over, the machines are really never that smart. And so there's always going to need to be people to help the machines. And hopefully what will happen is that people will feel very much upskilled and they won't be doing so much kind of manual labor, whereas the computers can take care of that because frankly, they really don't care. And they're very good at repetitive things. And so why not task them and give them that application and then sort of add our expertise to the way that it conducts itself in this particular environment. Now, the other thing I like about these types of solutions is it gives us the opportunity to record the information itself. So we might want that for product liability reasons, or we might want it just for learning, or we may need it in the future when we're trying to work out if a change in a particular process has had an impact. We'll have the historical information. Now, you know who's really good at doing historical information, and this is coming to my point about sometimes why we need to have a lot of information or a lot of data. Aircraft are really good at it because they have something called a quick access recorder that stores an enormous amount of information. You can have maybe 10, 20, 100 flights of information that can be recorded there. Generally, it ends up being in kind of like at least the gigabyte range, if not terabyte range of storage that it can provide. And it's extremely verbose and it's very fine grained. So when we think about that sensor example that I gave before, which I think was like a speed sensor that you would see kind of sit on top of a flywheel, that would be no problem in this circumstance because the type of sensing that you have on an aircraft is vast. So we would be able to get down to things like exhaust gas temperatures and so on without any question. And we would have, importantly, a time series of that information that we can then put into one of those tools that would help us understand if there is anomalous behavior, but it would also help us understand what forward-looking performance would look like. Take it one step further, and something that's very popular in this industry, if I'm not mistaken, was kind of invented by this industry, is the concept of remaining useful life. And one of the reasons why this is a very important metric for us in many regards is that it doesn't just signify when there can be a potential failure, but just rather in its operating life where it's just no longer going to be efficient. And so being able to define a threshold of where that inefficiency occurs is really critical. And those same types of practices can be taken forward in our industry as well. And generally it works particularly well because then we can make the determination of would the part still remain working until we can schedule service, or do we need to move service ahead because the amount of life remaining is actually short, and then we would have a service interruption in the equipment and so on. So one of the points I like to make here is that if we had the opportunity to kind of transform the industry, we would have these types of recorders in almost everything because it would give us a head start on the data itself. And it would also give us the type of insights that we need before we make that sort of step to go through remanufacturing. It would give us a full and complete view. And the analytical information would also help with overall focus. and perhaps even kind of profiling of the information to say how much it will cost us to go through remanufacturing and to what degree do we want to do an OEM component or not? Do we want to do a refurbished component or not? We'd be able to make those decisions very easily before we even touch a piece of equipment, whatever it may be. So to kind of wrap things up for you, I was thinking about how we would go about solving the problem if we had all of that type of information available. Now, with the example of your Airbus A380 that you saw there, it only has some of the information. And in fact, in this particular chart, it has more like what occurs during that phase of sort of maintenance and ownership. It has that information, which is an important part of the overall sort of data value chain. There's no question about that. But from an organizational point of view, if we were taking, you know, that aircraft through like a Schedule D, where we're just going to tear it completely to pieces and we're going to start replacing absolutely everything, or we were taking that Caterpillar excavator in and we're going to do a tear down of it anyway, what other types of information do we need to kind of work out overall what the impact will be to our supply chain, what the impact will be to our manufacturing, what the impact will be to the cost of the equipment when it goes back out. If it's an aircraft, it's sort of like, what is the overall sort of capital expenditure that we've put into our operating equipment? If it's that excavator, it's at what cost can, or sort of at what price will we be able to sell it back on the open market and still make money? In order to do that, we have to have sort of a much bigger connection to the enterprise information than perhaps would first be obvious. The way to think about it is that in remanufacturing, you want to go back to specification. And so part of that specification understanding is going back to what occurred in engineering on that piece of equipment in particular to know what that specification is. In some cases, that is really well known when we get the same type of parts that are coming in for replacement. But it's not always known or vastly known, pardon me, in the industry, especially when we see kind of replacements occur. So if we have sort of a 3-supplier approach for manufacturing, we may find that something comes back in that had an alternate part that we don't have very good profile information for. And so therefore being able to source that information back from engineering or back from manufacturing or procurement actually becomes really critical to understanding how we would go about doing a replacement. The other thing that I find really valuable about this type of sort of data value chain or sort of creating a thread between all the different types of information constituents is that it also gives us an understanding of what will occur at the end of the day. So we've got that view of sort of how many times was it sold, at what cost was it sold, or sort of what price did we accumulate, where and when and how was it used, and what likely is it going to be used going forward. It does give us a full and complete picture of the end game, not just tactically what's in front of us, which is to put something back together in the highest quality and lowest possible cost fashion. Finally, I thought I would make a couple of recommendations. I just had the opportunity, so I thought while I have the floor, so to speak, I'll share a few insights just about how we would think about transformation in this industry, and perhaps some of this might be some food for thought for you, or perhaps many of the things that you've already been thinking about. The first being that having the information to drive that type of assessment of condition and then using that as a method to then organize the way that we would go about a rebuild or the way that we go about remanufacturing actually is really critical. This is the way that an organization can make money, in our opinion, is the information does lead us to an assumption, sorry, it's not even an assumption, it leads us to something that's very determined going forward rather than having to make an assumption about what we will do or go through the exploration of what is required. On the other side of it, we kind of need to say, well, that's going to have to be a lot of historical information. So building that digital thread in an ideal world is absolutely what we would want to accomplish. But even at a sensor level, if we have the historical information where either we can create that just through running the sensor through kind of a test procedure, and or we were lucky enough to have something with onboard capabilities such as our aircraft, or we've got more kind of verbose information perhaps captured through a telematics program, that is the answer. We don't always have to have absolutely everything in that value chain. Sometimes we can just be very tactical about what is required and what we need. So one of the recommendations I have, of course, clearly as an industry is that we start to think about the data problem as something that we want to solve in the product itself, is that at the moment, we kind of obsess over the sort of, the quality of the particular type of equipment that we're putting into the market, whether it happens to be a backup power generator or whether it happens to be an excavator, an aircraft, or vehicle. So we like particularly put a lot of time and effort into that. But I don't always see a lot of time and effort put into just having the type of kind of core data system that helps us with many of these other objectives that we have in the organization. And then finally, I would say that there is a huge advantage in taking this type of compute problem to the cloud because there is scale that can be afforded there. So the storage is very cost effective, the compute is readily available when it's needed, and we're not then concerned suddenly about where is the information and how do I get to it, because we've now made it sort of a global standard for how people can access the information in a secure and safe way for them and take advantage of the knowledge that they can obtain through that information themselves. So I would just like to conclude by just saying thank you once again. I really do appreciate very much the opportunity to come and speak with you. It's always a pleasure to do so, and certainly looking forward to any follow-up questions. And thanks once again.
Excellent. Thank you, Simon. Great insights there. I'll invite the panelists to come on audio and video, and we'll get into our Q&A time. All right. Well, I thought that was a great mix of background and application. So I'm looking forward to the next part of the webinar. Let's get started. I think many of you spoke to this, but let's just sum up a little bit. What are the characteristics of problems that make good ML/AI type applications? Simon, Jim, Dave, have thoughts for that one?
Come off of mute first. How about that? This is Jim. Thanks, Todd. I mean, I'll just define that, at a more of a macro level, maybe the particular technical components of what could make one better than the other. But I would say again, thinking about where are the where can the value be unlocked in the overall process to enable, more customer success, more customer value delivered through the entire process, as opposed to which technical component to drive or why it would fit there. Where the best fit on unlocking the business potential would be one of those filters I would put against the first priorities.
Yeah, Todd, maybe I could add a little bit there is that, I would maybe break it down into two categories. I'd say one where we have time-based information. I think that's really conducive to just data analytics in general. That's when we can get things like anomaly detection and we can start to do prediction on the information. So, and usually we see that in like sensor information. So if we can record it, get the values from it, then we have a situation that's good. The situation that's challenging is where we get maybe just like a diagnostic trouble code. And they happen infrequently, or we see the same one repeated over time. That one's a little bit more challenging because historical information doesn't give us an opportunity to kind of learn what it would look like going forward. So that one's a slightly different data challenge, not as conducive, I would say. And then on the other side, I think anything you can look at basically through a camera, I think is absolutely a match 100%, because there's so much that can be done just with the technology by itself. And something I actually really did like from my colleagues, my fellow partners at IBM, was the sort of concept of taking acoustic information as well. I think that's a really good time series type of exercise. And I think with a camera, you can get both. So you can get audio and you can get video. It gives you an opportunity to maybe get two types of data feeds all at once. So that's kind of how I think about it.
Yeah. Good. Other thoughts there?
One other thing just to add on that, I would say there's some applications where it doesn't make sense to try to use machine learning or AI, so don't try to force it for every problem. If your problem can be solved with a robotic arm just doing the same path over and over again, then pick something up and place it in something. Don't try to force machine learning or artificial intelligence into that, because it doesn't need to be there.
Right. Good. Thanks, Tyler. Let's talk about the business case. What are typically the cost drivers and business benefits that factor most strongly into this sort of business justification that we often need to provide if it involves significant capital or expense, for example? The IBM and Google teams probably have the most experience in framing or helping organizations frame those business cases. You guys have thoughts?
I sure do. But Jim, do you want to take a crack?
No, go ahead. I just didn't want to jump in front again.
Yeah.
Simon, but please.
We were both looking at each other, being nice and polite, like, oh no, you go first. No, you go first. Yeah, I think, I mean, there's quite a lot to talk about here, to be honest. I think kind of pride comment about, you can't solve, kind of world hunger nor world peace with AI or ML is a really good point. I think you have to be very selective about where it's going to give you the biggest impact. And there's a whole lot of factors around that. I think one is kind of like the cost of acquisition. I think that's always been a really big question for many. In the aircraft programs that I've run, the cost of acquisition is actually quite high. There's a lot of aircraft are not sophisticated enough to kind of publish the information directly to the cloud or even directly to a base station. What they receive is kind of minimal. It's sort of, somewhat, spaced out every 2 minutes, every 5 minutes or so, kind of, summarized data. When we're trying to get something that's more, comprehensive, the cost to acquire it is really high. So then that does become a question of, well, what's the outcome? Well, on aircraft, you want to go through that kind of procedure because what you can learn is really critical for safety, and it's also kind of critical for what the knock-on effect can be of something that can occur on an aircraft that's bad. Even something not mission critical or safety critical can still, cause it to be grounded, which is not good. That becomes then a question of sort of what type of product is this at the end of the day, and so. If we're talking about something like a cell phone, maybe there's not as much of an ROI case there because it's not kind of mission critical. The type of things that are going to occur to it would be annoying, but it wouldn't stop it from working. Maybe the case there is a little bit more marginal versus something that's kind of like complicated and stiff, mission critical for someone, and then it becomes much more of a slam dunk. I would say the biggest challenge for people is actually working out what this is. So that there's no shortage of technology. We can apply it every which way, but it does become a question of, do you really need it to give you an outcome that you couldn't do any other way? And can you do that then at a lower cost? That's when we have a match. And sometimes that requires a lot of people. We see that with vision inspection. If they're erroneous, people get tired, so they make mistakes. The cost of the technology pays for itself in a really short period of time. So maybe I might have said a bit too much there, but go on, Jim. I'll hand it over to you.
Well, I very much agree with those point of view, but I'll kind of pile on to that some other dimensions that we've seen people think about and support. Kind of where the business case or how the value flows, and kind of the first and foremost often should be right is either the safety side, whether it's the product and the product implications, but as much so within the workplace itself, right? Where are able to prevent recordable incidents and worse in the work environment, right? That is a business driver for people. The other, kind of guide in that business value piece is, David alluded to it in his comments, is early in the process as we wish we could have detected or known. So instead of flowing defects or rework through a system further, how far upstream could it get if we look back on it, if we had only known kind of thing, then poking at exploring where could we go seek that knowledge to turn it to the data, to turn it to knowledge and insights that we can act upon. So as far upstream as possible will eliminate a lot of the redundant and subsequent waste downstream. And in particular, from the customer perspective, right? We can retain and satisfy customers from not shipping to them, but obviously not having to detect at the end if we can work it on the airproofing methodology early in the process to get the right things. And then kind of the last one that flows from that, a little bit counterintuitive, is the technology application as a labor saving device. That's generally good as well, given scarcity of people and the economic impact from it, but it's also a result, right? Thinking about how do we not drive for that, but how do we deliver the safety and quality internally and externally first?
Good, thanks. Other questions or comments there? Well, all right, so here's probably a two-part question. What are the perspectives here on how to get started? I suppose on the one hand, you could say, look, let's go identify a few little pilot cases. We're not going to boil the ocean. We just want to go demonstrate this, and then we'll make more of a broader plan. Or you could start high level and say, hey, what's our master plan here? And then develop that, and then have a very deliberate and thoughtful execution. What are the perspectives?
Hi, Todd. This is Dave Meek. Can you hear me? Yeah. So what I see in industry is many manufacturers, reman companies doing the small little proof of concepts, the tinkering in the corner. It's great for self-education for the engineers and maybe people that are learning data science skills. But it doesn't change and have that impact that senior management wants. They want to get 5% reduction in costs. They want to get 125% increase in throughput. They want to improve OEE by 20%. And the only way you do that is you apply these technologies, not at one little action at one little work center, but you deploy these across the plant, across the entire value stream. And oftentimes it's more than one of these types of technologies working in tandem. And so what I've seen is companies either do a quality intelligent workflow across their value chain, or they do a optimization throughput, or they do a reliability asset optimization all the way through. And that's how you get the number one, the real dollars that the CFO adjusts his or her glasses with when they see the figures. And quite frankly, if you do it upfront with a proper business case, you can eliminate the midlife crisis that these projects often get when they've spent a lot of money, they haven't shown a lot of value, and they question continuing it.
So I'll add a little bit to Dave's comments. I agree with Dave, but there's another side coming from industry. What I've seen is that if you don't start small and demonstrate its value and go to the other side and start big, then you may be investing too much. And then, like Dave said, people will ask questions. And problem with going too big is that to get the proper value out of this AI or these data analytics based decision making is that it is not only the analysis part that's telling you what to do. You almost have to change your culture of the company, how you service your machines or whatever your products are. For example, if you're applying into services, your analysis may be predicting that, hey, this part fails at these intervals. But a lot of the time, a tech rep may go to a machine and change parts because he or she doesn't want to go there again in the next few months. And that kind of changes everything in the data side. So we have to be careful about that unless you're changing the execution, implementing the AI piece in the large scale will not give you the value. So that ecosystem has to change within the corporation to get the proper values. If you cannot do that, you might as well start small and change, adapt over time as you're developing, getting more information out of the AI system.
Just to kind of provide a different perspective, I haven't spent many years in industry in a long time, so I kind of look at it. There is a collection of problems. So there are some problems, like Tyler said before, that are well suited for some traditional methods. Others are well suited for machine learning. So identifying the right problem, and Simon mentioned before the cost of data acquisition. So if data already exists, that's an excellent situation. If data can be inexpensively attained, if the knowledge that's required to be attained by this machine learning system is very straightforward, how to impart it into the learning or training of these machine learning models, those are good cases to start.
And Nenad, I'll pile on that just for a second, and strongly agreeing with you in the idea of, whether it's my opinion, whether it's point solutions and or the whole system. Organizations that kind of go slow to go fast and make their master plan and understand where those key leverage points are first, then can make a more informed decision about breadth. So we would say, make sure you get that total vision in the lean terms, if you would, that total value stream, flow of knowledge, information, products, sub-assemblies, people, et cetera. Then make the informed choice around what are the longer levers for you, wholesale or narrow. But start with the plan, or in the Coveyism, right, with the end in mind.
Yeah, I think I make a quick comment too. We really advocate experiential learning. Is that we would say if you can stand something up quickly and get runtime with it, you will learn from that experience, which will give you an indication of what to do next. And I'd agree. I think having the master plan is really critical because you do need to organize yourself. I mean, we're a real business here. So, the cost of resources alone becomes a concern, even in this context. Let's add up all the salaries of the people here today. How much did it cost? It's sort of, you've got to have that consideration. But I would say on the flip side of it, if we don't try it and see where we can go with it, then we won't be able to innovate either. And just to give you a quick data point for that, we implemented a system for automotive manufacturer. It was there for a very specific purpose that they had planned. But just, if you like, on our own, we captured quite a bit more data. And then when we provided a secondary analytic for that, they identified an endemic problem that was in a machine that they actually had no idea. They thought it was just the performance of the machine. They didn't realize that they could improve it just by swapping out a component. That type of insight made them believe that there would be better use of the data that they already have and that they should expand the program that wasn't in scope. So I like to kind of run both ways if I can. I do like the master plan, but I also like some of that experiential learning. I think it can be very helpful.
Yep, good, thanks, good insights. So real quick, what are some of the fail modes? So Dave, I appreciate your reference to the midlife crisis there, and actually heard about that very thing in a different company. So either in a broader initiative or on specific projects, what are some of the fail modes that project planners or leaders can anticipate and mitigate?
So the number one thing I see is trying to scale a successful proof of concept to an enterprise application and having to start from scratch. So, it's using open source, but not understanding the architectural either limitations or other foundational technologies that enable it to be rapidly deployed throughout a plant. And to give you an example, our welding example, the first plant has 600 weld stations. And we do most of the inferencing at the edge of those weld stations. So, we can't send everything up to the cloud. Instead, we use the cloud for training. We send the trained models back to the line, and we use edge servers to actually inference right in time with the actions. Having that architectural view to be able to do this at scale and make it affordable at scale is very big. Oftentimes people are doing Raspberry Pis and simple stuff, and then they basically have to start from complete scratch again to architect it appropriately. The second challenge that I see on it is the immaturity of many companies with managing IT in the OT space. In this area, OT historically has had an air gap for security reasons, regardless of the enterprise systems or the internet. Their on-site systems, they can still push products out the door. Most of these technologies are IT based. There's a lot of discipline and security with them. OT systems oftentimes have been managed and implemented and maintained by tribal knowledge of the engineers at the plant. And so we see companies trying to mix these two areas of technology. There's right ways, best practices, security is paramount on how you do this. And there's also different methods. We see people using 5G sensor networks to gather data independently from the data that's provided by the OT network. We also see DMZs in oil and gas. That's very popular to have mirrored historian servers that are sanitized so that you can get the runtime data without actually connecting to the lines on it. So the first is architecting the scale, and the second is IT/OT integration maturity.
Excellent.
One of the failure mode I would say is that trying to apply these methodologies without having proper domain knowledge. As Nenad explained, with the Python ecosystem, the cost of entry is pretty low. So we cannot just analyze this data blindly. Somebody who's doing that should know. Every technology is different. Every industry is different. Their business case is different. So they have to do the analysis in the perspective of that domain, or else it'll be, and there are failure examples of that.
Yeah, I have one kind of adjacent to that, which is, you know, giving your tech vendor the fringe case. It's the 1%. And I know as engineers, we love to do that. It runs on the methodology of, if you can solve this one problem that no one has ever solved in 20 years, I will scale you up and make you so successful in my plant, my enterprise, global domination, that type of thing. Please don't do that, because the reason why it hasn't been solved in 20 years. So instead, if you want the experience of how to do this the right way, I would say focus in on some of the areas which are in the middle ground. They're challenging, yes, because of the technology that you currently have or process or practice. Focus in there. The easy ones, I think we all understand that we could do those. So maybe there's not as much value in going that direction. But try to go into the middle ground. Go for sort of the 40% that sits in the middle that has been difficult today, rather than trying to go after the impossible mission. I think you'll find in many cases the impossible mission, there will be a path to get there, by the way. We're not ignoring it. But I think rather than saying, you know, how are we going to excavate something on the moon, I think we should worry about how to get there first. And so that's sort of the way that I would recommend thinking about these types of programs, is kind of get there first and then start to kind of grow in either direction.
Appreciate that.
It's
great.
I'll
great
throw one.
insights.
I know we're running up against it. I just want to throw one thought on, because I'm really passionate around the topic, as you mentioned, the failure mode piece, or where are the risk factors for the organizations. I would often say, you know, let's not forget, you know, and organizations do sometimes in the pursuit of these applications, the people side of the component. And once we've got data and information and converted to insights, do we have the problem solving capability that we provided to the people, so the human element can make it different, better, faster, cheaper, safer. So, you know, ignoring and marching past or with on, but again, a foundational element in my mind around the people capabilities that use this AI and ML.
Yeah, thanks. That's great. Two more questions, maybe a detailed one for Tyler, and then a wrap up on the life cycle digital strategy. So Tyler, I was intrigued by the weld path planning. Can you comment on to what degree the process could, you know, semi-autonomously handle a pretty wide mix of different size and orientation of welds? Or is each one its own little project? Yeah, go ahead.
For that specific project, I think we found we were probably overtraining on a few specific samples that we had. So they'd be really good at recognizing parts that are almost in that exact same shape. But I think that just comes down to a data problem, as we've talked about a lot here, is like you need a wide breadth of data to collect this, and the wider breadth of data that you collect to begin with, the wider breadth of application you can have in the long run.
Maybe a quick follow-up. Are there some obvious other process types that would be a good extension of the sanding example you used?
Yeah, I think with both of these applications, there's just specific applications of a vision system on a targeted system. But in particular with the sanding, it's a visual classification of, is this waypoint process finished? So it doesn't necessarily mean it has to be for sanding. It could be for painting or any other material removal or addition or any sort of processing that happens on the process.
Excellent. So Simon, you provided a great view of the life cycle digital thread, and I can appreciate how if an asset is captured, throughout its life cycle, that's easier to maintain. Are there any thoughts around, market forces or other forces, I don't know, regulatory forces that would facilitate maintaining this in the future, recognizing that there might not be a single owner of this thread, but there's going to be other people that contribute over time?
Yeah, Todd's a great question. The insights that I have, all kind of like the learning, and most probably even in just like the last 2 years, I think it's completely changed from what I thought it was even sort of 3-4 years ago. But there is so much information out there that it's almost impossible to say we should just try to have an industry standard that gives us an overall enterprise ontology or a factory ontology, whichever way you want to think about it. I actually think that might not work. And having looked at different types of programs before, looked at step protocols and so on, they do a really good job of getting a definition, but unfortunately they age, which is why we're all involved in these standards anyway, is to try and keep the evolution of them going. But in a way, I think it would be better just to say the information is out there and we will build the connection between the information and use it as we need it at that moment in time for the environment of our business. It's a very different approach because we're kind of saying you almost don't need to be so organized with your information to build your digital thread. You just have to know the different sources of the information in order to bring it together. And one technology that we feel has been really very helpful for this is thinking about the development of a knowledge graph, because it thinks about the relationships between the data very differently. You can create the relationship without having to have sort of common data that would normally be there for a relationship. You can just sort of infer that, between here and there is a relationship, I'm going to name it, rather than part number is over here and part number is over here, and so therefore join. When we think about it that way, you can actually build out these digital threads really quickly and you can make them dynamic. So I think that that's most likely going to be our path forward, is to sort of say, let's just keep the data chaos if you want. There is nothing wrong with that. And let's just have sort of like a master view and relationship management on top that will be our path forward. That's what we will maintain.
Excellent, thank you. Any other last comments? All right, with that last thought, that data chaos may persist in the future. We certainly want to thank all of our panelists for joining today. Great discussion, great presentations. Thank you for the audience for participating as well. And on behalf of the RIC, we wish you all a good day. So long for now. Goodbye.